So we're looking at Unit 2.23, the binomial theorem continued, and we're going to kind of review the binomial theorem. I'm going to talk a little bit more about how we actually want to write the binomial theorem and how we compute the coefficients, and then we'll try a couple of examples, just to kind of cement in our minds how this works out. Okay, so we want to look at the binomial theorem once again, and I'm just going to talk about couple of ways that the coefficients in Pascal's triangle make sense in terms of what we're doing. So let's go ahead and just rewrite the binomial theorem once again. Remember, my first term, what I'm going to do is, if let's say my degree were 3, I'm going to use the third row of Pascal's triangle to find the coefficients here. So I'm looking in the nth row, and I start out in the 0th column. And then, remember, I'm going to multiply first a times all the other a's, so I'm going to have a to the nth power, and b to the 0th power. And then I will move on, and in the next coefficient, I'm going to still be looking in the nth row, but I'm going to look at the next column to the right, the first column. And that will be a to the now n minus 1, b to the 1. Okay, and now we'll continue moving on, and I'm going to skip ahead to the second to last term. So the second to last term, I'm still looking in the nth row of Pascal's triangle, but now I'm in the second to last one. So if you consider, think about this row 2 here, if n were 2, if the exponent were 2, my last term is going to come here on the far right, so my second to last term will be the one right before it. So if this is my nth column, the second to last will be the n minus 1th column. And this will be a to the 1, right? I'm almost all the way at the end, and b to the n minus 1. And then the last, I'm going to have the nth row, nth column, a to the 0, b to the n. Okay. And so hopefully that's you remember that from class today, and now you can we want to think about, where do these coefficients come from? Why does Pascal's triangle give us the coefficients for each term? And so there's a couple ways to think of it, and let's just first remind ourselves what the definition is. So n choose k. What that is it's asking you how many ways can you choose k things from a group of n things. Okay, so definition of that is n choose k. And Pascal's triangle happens to allow us to compute that. So if I'm looking at, let's say, and remember that the n is the row, and the k would be the column here. Okay. So if I think about, 2 choose 1, right here. How many ways can I choose one thing from a group of 2? Well, Pascal's triangle gives us that, right? There's one way like that, and one way like this, right? So there's actually 2 different ways for me to choose one thing from a group of 2. Okay? And so that's kind of the way that we want to think about it. If I were, let's see, 3 chooses 0, for example, right here, how many ways can I choose nothing from a group of 3? Well, there's only one way. I just take nothing out. And so all I'll be left with is just one way. And to help us get kind of more intuitively to understand how this works, I want us to look at the example where we're taking a plus b cubed. Okay, so I have that right here. And I want you to just pause the video and go ahead and use either the binomial theorem, or you can just FOIL it out and multiply it out, and go ahead and simplify as you need to, so that you have all the terms written out. Okay, so I hope that went well. I'm going to write it out using the binomial theorem and explain where these coefficients come from. So I'm looking at the third row, right? I have an exponent of 3, and the first term is 3 choose 0, a to the third, b to the 0th, and then I'll go ahead and I'll just do the first two terms. Now I have 3 choose 1, a squared, b to the first power. Okay? And we could continue, and we might look at a few in a second, but let's think about why this 3 choose 0 makes sense. So notice that this is the first term, a cubed. How many different ways can you make a cubed by multiplying these three binomials? Well, notice there's only one way. The only way I can do it is take this a, multiply it by this a, and then multiply it by that a. There's only one way. And the way that we can kind of think about this is if you have 3 buckets here, I have 3 binomials, how many ways can I choose 0 b's out of them? Okay? So in order to get a cubed, I have to pick an a from each one to multiply. And so this is really saying, a way to think of it is, if you have 3 different binomials, how many ways are there that you can choose none of the b's? In other words, all a's. So a times a times a. And if I move on to the second, so first off, that's 1. Okay. So this would just be a cubed. Now the next one, 3 choose 1. Okay. Well, here I'm saying I only want to choose one b. Okay. So I have 3 buckets. I'm going to pick out of each bucket. I want to choose b from only one of them. So b to the first power, and I'll have a squared. How many ways can I do that? Well, I can go a times b. I could do a times b. Or I could do a times b. There are 3 ways here. 3a squared b. So you can kind of think of this 3 choose 0 or 3 choose 1 as I have this many binomials, and from each one I want to choose, this many total b's. So I want to choose 0 b's. I want to choose 1 b. Okay? And those are the number of ways that you can choose that exact situation. Okay? So we're going to take a look at how do we actually compute this in a little bit, but for now we can use the Pascal's triangle in order to compute any binomial that we want. Okay, the next thing that we're going to look at is a simpler way to write this all out. So let's take a look at our expansion again, what happens when we expand a binomial to some power. And notice that each term that we're adding, it's very similar, right? So there's only a few things that are changing with each term, and I'll kind of want to note those. So as I move from term to term, I'm always looking right at the nth row of my triangle, right? That's where I'm getting all the coefficients from. The only thing that's changing is the column that I'm looking at, right? The number of b values that I'm choosing. And so this is changing here. This will change, right? This will change, this will change. But the n's going to stay the same. Okay? And notice that in each term I have a to some power times b to a power. And the a and b are always going to be present. The only thing that's changing is the powers itself. So what I can do is I can actually write this in a much simpler form. Think about what you're trying to say. You're trying to say, hey, keep adding terms that look very, very similar, and here's what you need to change, right? And so we want to be very specific about what we want to change. And we can use sum notation. That's S-U-M, not S-O-M-E. Sum notation. So this is the Greek letter sigma. It's analogous to the English letter S, and so we use it to represent a sum. And we say is, hey, we want you to start the sum at some value and want you to finish at another value. And every time you're going to increase that value and you're going to add that particular sum. So let's think about the sum that we're adding. Well, every time we're going to have n choose something. We're going to have a to some power, and we're going to have b to some power. And then we just got to think about how do we order, how do we count both the column we're looking at, the exponent for a, and the exponent for b. And so usually with sums, we start at 0. So we'll define some variable k, and we'll say, hey, start the sum when k is 0. So let's just think about it. What do we want to start at 0? Well, we'd like to start looking at the 0th column, so we'll just plug in k there. because what will happen? Well, k will start at 0, and every time k will increase by 1. That's the way that the sum works. It says start at k equals 0. And what do we want k to finish at? Well, look at all of our sums. We want the last column we look at to be n. So we'll say start when k is equal to 0, and finish it when k is equal to n. Okay, so if I were to add this, the first term is when k is 0, so it'll be n choose 0, and then I just have to figure out the exponents here. The last term would be, I count all the way through, so I'd do when k is equal to 1, it'd be n choose 1, and I'd add that to what I've already gotten, and I will finish when k is equal to n. Well, now let's think about the exponents here. So we want a, when we start off, we want a to be raised to the nth power, right? So we want to start at n, and each time we want it to decrease by 1. Well, this is interesting. K is going to be counting by 1. That's the definition of the sum. It'll count by 1. Okay? So if k starts at 0, well, when it gets to 1, we want a to be to the n minus 1th power. So we can just say, take n and raise it to the n minus k power. Right? So that way, when k is 0, this is a to the n. When k is 1, it's a to the n minus 1. And when k is n, think about it, it's n minus n, which is 0, and that's my last term. What about b? Well, I'd like it to start at 0, and I want it to work all the way up to n, just like k. So it'll be b to the kth power. Okay? And so this is a shorter way of writing out everything that you need to do to expand a binomial. Okay? And think about it, if you just work through it, when k is 0, this gives us the first term. So I'll write that term down, k is 0. Then k will become 1. I'll evaluate this when k is 1 and add it to what I've already gotten, second term. Okay, so go ahead and pause the video, just kind of go through and think about what this would look like when k is 0, k is 1, k is 2, k is 3, and you'll notice that you're just adding up all the terms that we've already talked about. We're going to take a look at a couple of examples, and before we do that, I want you to practice using sum notation here to actually write out the expanded form of the binomial theorem. So I'll get us started. First we start when k is 0. So the first term will be n choose 0, a to the n, because it's n minus k, and k is 0, a to the n, b to the 0. Okay. Next term, well, now k is 1, so it'll be n choose 1, a to the n minus k, and k is 1, so n minus 1, b to the k, and k is 1. And you could keep going on. So you should see how it's really the same thing. This is just a shorter way to write it. All right, go ahead and pause the video, try both of these examples. We'll talk about them briefly, and then we'll take a look at another couple of examples. All right, hopefully that went well. Important to remember what your a and b values are, and also note what your exponent is. And I always like to find it helpful to just kind of input those values into my summation notation so I can sort of go through and see what I'm going to be doing. So I'm going to be taking the sum. I start when k is equivalent to 0, and I'm going to finish when k is equal to n, and n here is 4. All right? And every time I'm going to be using n, which is 4, and I'm going to choose a certain number. I'm going to choose k from that 4, and then I'm going to raise a, which in this case is 5, to the n minus k, which is 4 minus k, and b to the k. Oh, but b we know is x, so we can go ahead and just write that in as x. Okay. And now I can go through and I can write this out. So my first term is when k is 0, it'll be 4 choose 0. Five to the 4. Next term is going to be 4 choose 1. 5 to the 3rd, x to the 1st. 4 choose 2. 5 to the 2nd, x to the second, 4 choose 3, 5 x to the third, and finally 4 choose 4 x to the fourth. And we can simplify this further because we can use Pascal's triangle to pick out the coefficients. So we'd go look at Pascal's triangle, you go to the fourth row and just go column by column. Okay? And so using that, we'll have 5 to the fourth. You can simplify that if you'd like, but we can just keep it as 5 to the fourth. 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. So if you haven't done so already, go ahead and move through and simplify this out, and we'll check back in a second. Okay, so 4 choose 1 is going to be 4. So we have 4 times 5 to the third times x. Now you can compute 4 times 5 to the third if you want, or we can just leave it like that. 4 choose 2 is going to be 6, and we have 6 times 5 squared. Well, 5 squared is 25, and 6 times 25 is going to be 150, so we can go ahead and compute this one out. 150x squared. 4 choose 3 is going to be 4 again, so we have 4 times 5, which is going to be 20x cubed, and 4 choose 4 is 1, so we have x to the fourth. And that will be our binomial expansion. Alright, at this point, if you didn't quite get to number 2, go ahead and pause the video and try number 2. I'm just going to post the solution in a couple seconds and let you kind of work through any issues that you see and figure out where you made little mistakes. Alright, so there's the solution. Go ahead and go through it. Here's my work above. This is where I just inputted the values, and then you can go through and check your work to make sure that you got it correct. We'll put a couple more problems on the next page for you to try out. Alright, last 2 problems for you to try. Go ahead and expand 2 plus x to the 10th using the binomial theorem, and then use the right triangle identity to find the side lengths of a right triangle where at least one of the sides is greater than 150 units. So you might want to look back at your notes from a couple days ago to remind yourself of this polynomial identity and use that to create your right triangle.